human-rated spacecraft called Orion, built in 3 parts. The crew module, where up to 4 astronauts will live and work throughout the flight. The service module, with life support systems for the crew and its own engine and fuel reserves. And a launch abort system, with engines capable of pulling the crew module to safety during launch should anything go wrong. To accomplish the task of launching our crew and heavy payloads, NASA is building the Space Launch System, comprising of a cargo hold, an exploration upper stage, a massive core stage, and 2 extended solid rocket boosters. Altogether, this is the world's most powerful rocket, and it exceeds the legendary Saturn V of the Apollo era in numerous ways. Sitting on the launch pad, the entire rocket, fully fueled, weighs just over 6 million pounds, 5.2 million of which is just the fuel. Once ignited, there was no stopping what comes next. All 4 Rs25 engines and the 2 solid rocket boosters come to life, thundering our crew upwards. 2 minutes after ignition, the solid rocket boosters are spent and released. 8 minutes after launch, the core stage is depleted and separated. The upper stage fires briefly, placing Orion into a parking orbit around the Earth. Here, the crew reconfigure the spacecraft and check systems to confirm everything is ready for deep space travel. With a go from mission control, the crew reignite the exploration upper stage engines to leave Earth entirely. The exact timing of this maneuver is critical to reach a speed that can escape Earth's gravitational pull, but also put Orion on a course that will intersect the Moon days later. Once this burn is complete, the upper stage of the SLS is jettisoned and the crew aboard Orion coast for several days toward all that awaits them at the Moon. Approaching the Moon, we see the fundamental differences between Artemis and Apollo. Instead of requiring Orion to serve as an expendable lunar command module or to carry a constrained lunar lander, the Artemis missions will take advantage of a different approach: pre-staging. Everything needed for lunar missions will be positioned in advance by commercial and international partners. This includes rovers, science experiments, and human-rated systems on the surface. But it also includes a dedicated lunar station in orbit around the Moon called Gateway. Here at this station, we can pre-stage a robust lunar lander and establish a strong communications relay. Designed with open standards, the Gateway can be expanded as new missions and partnerships develop, allowing multiple human missions on the Moon at the same time and enabling ongoing science to be conducted even between human missions. The Gateway is also capable of adjusting its orbit to allow access to every part of the Moon, something the Apollo missions could not do. But the real key in this approach is placing Gateway in a unique halo orbit to perfect the maneuvers needed for Mars missions. And with the growing list of commercial and international opportunities, Gateway is the ideal hub between Earth and all that lies beyond. Returning to our crew as they approach Gateway, the Orion must match the elliptical orbit of the station in order to successfully dock. Once on board, pre-selected crew members transfer to the lunar lander, while those assigned to Gateway remain on station. The lunar lander system itself is built for 3 unique steps: descending from the halo orbit of Gateway down to a low lunar orbit, descending from low lunar orbit to the surface, and once the lunar mission is complete, launching from the surface of the Moon and ascending all the way back to the orbiting Gateway. Once back aboard the Orion spacecraft and undocked from Gateway, the crew fire their engine once to break out of the halo orbit, and once again to sling the spacecraft around the Moon, placing it on a multi-day trajectory back towards Earth. As they near the end of this journey, the service module is released, and the crew module is oriented heat shield first. Entering Earth's atmosphere at 25,000 miles per hour, the friction of air slows Orion considerably, while also subjecting it to temperatures of 5,000 degrees. With the Orion now at just 300 miles per hour, a series of parachutes uniquely tested and produced for this moment deploy, decelerating the craft to just 20 miles per hour for splashdown. With each successful mission, Artemis ushers in the next wave of men and women to explore our Moon and prove that together we are ready to go beyond.
At NASA, we have always answered the innate call to go.
With Artemis,
we
are going to stay.
Proving that humanity
can live on the moon,
Mars, and other worlds,
and share the wonders of the solar system with all.
Our story is one of people.
All those who make this journey possible.
From advocates across communities,
to companies across industries,
to countries around the world,
we achieve this collective endeavor.
Our efforts create impact for all.
Technologies that revolutionize industries.
And jobs that bring prosperity to people.
The discoveries from space
benefit the way we live on Earth today.
And those from the moon
will create a better future
for generations to come.
But to do that,
we must go.
Hi, I'm Chell Lindgren.
My name is Raja Chari.
Kayla Barron.
Kate Rubens.
Hi, I'm Christina Cook.
NASA astronaut Joe Akaba.
Jessica Amir.
Woody Hoberg.
Anne McClain.
Stephanie Wilson.
My name is Johnny Kim.
Nicole Mann.
Victor Glover.
Jessica Watkins.
Hi, I'm Matthew Dominic.
Jasmine Morbelli.
Frank Rubio.
Scott Tingle.
This is what we do.
This is what we will do.
Let's go.
We go to the moon to learn how to live on other planets.
For the benefit of all.
Space Launch System is the next newest, biggest rocket that we're going to build, and it's not just a replacement for the Space Shuttle. This rocket is going to carry us much further than the shuttle would go. It's NASA's next big rocket for deep space exploration.
The SLS is a national capability that provides a unique access to space that America has not had in 40 years.
A large launch vehicle like this really opens the door to destinations beyond. It's not limited by destination. It's only limited really by imagination.
What we're focused on here at this center is the propulsion system. And that consists of 2 solid rocket boosters and a core with some tanks that feed some liquid rocket engines in the middle. And then the astronauts sit on the top in the Orion spacecraft.
One of the things we recognized for SLS is we had to be affordable. So we had to do things differently, more efficiently, and smarter.
We're all conscious about saving money, doing it more affordable than we have in the past. But at the same time, we can't sacrifice reliability or safety.
The system uses a significant amount of heritage hardware, which is things that we've evolved from the Space Shuttle program.
The Space Shuttle had 2 kind of candle-looking things, which are the solid rockets. Those are kept, and those are used on SLS.
We've added a segment to the 4-segment solid rocket boosters that we had on shuttle. That gives it more power, more thrust, and it helps this larger rocket get off the ground. What those boosters are for is just to get you going. They burn for a couple of minutes, and then they fall to the ground. Then your liquid engines, you're up high enough, your liquid engines can carry your vehicle to as high as you want to go, and if you have additional stages, like we're going to have one, then you can go further out into space.
Right now, the inventory that we've got consists of 14 engines that have flown on shuttle. We've got 1 engine that was assembled and still needs green run testing or certification testing. We looked at all the spares. As we collected the spares, we determined that we could assemble a 16th engine. So we'll have 16 engines that we'll be able to use for flight.
We are making tremendous progress. We've got all of our prime contractors on board. We're testing engines, we're testing solid rocket boosters, our avionics systems.
J2X has recently set a record at Stennis. When we were testing, it was the first liquid oxygen engine to get to a full duration test in 4 tests.
We were developing this booster under the Ares program, and we're moving that into the SLS vehicle. The motor itself has been through 3 development firings, which are full-scale motors tested out in Utah, and we've gotten a lot of good data, engineering data from those tests.
This is an adapter that goes between the bottom of the Orion capsule and the top of the Space Launch System rocket that we're developing here at Marshall. It's been specifically designed to give strength to the adapter so that it can take the loads in flight and still be lightweight. This shape started out as a series of flat panels. The isogrid pattern was machined into the surfaces. Then they were formed, it was called in a process called bump forming, to make them into the shape that we need here. And we weld 3 of these segments together to form the cone that you see behind me.
We just delivered the first crew module to the O&C building at KSC. We've started a lot of the parts onto the outside of the CM, and we've actually put it in what we call the bird cage, so we can locate all those an inch to make sure that everything is going together okay.
Putting wiring inside of it, putting tubes for the for the propulsion system, putting valves and pumps, and so all of that happens in stages right there in the O&C building.
We have on contract with USA, United Space Alliance, to build our harnesses. They're set up shop in the O&C, and so their little shop delivers to the big shop.
Thermal protection is very difficult in re-entry vehicles to test and to model. I mean, really you have to fly it to really understand what's going to happen. We're building ceramic thermal insulation tiles for the back shell of the capsule. We're building thermal barriers for the capsule, and we're building multi-layer insulation for that capsule.
I'm the heat shield design lead. So we're designing and building the heat shield for the future Orion missions.
The heat shield right now is in our big 20 by 20 router. It's a 5-axis router, and right now it's machining the interior bowl, if you will, of the heat shield.
To cut out that heat shield on the router could take weeks of machine time running multiple shifts.
It's the biggest heat shield ever constructed.
The other component is the heat shield skeleton, so that's the piece of the titanium substructure, the backbone that makes up the carrier structure itself.
Another unique thing is all the hand drilling that we're doing. So it's not automated by a router in this case, and it all has to be hand drilled by technicians on the inside.
200 plus titanium parts, all match drilled together.
So we have a tool that puts all the pieces in the right spot, and then we drill and high lock them all together.
MCC is transforming from supporting Space Shuttle and Space Station to a platform that will support Space Station and MPCV or Orion.
In order to adapt to the future, we need to go to a more modern system.
KSC will operate the vehicle all the way up until launch. We'll operate the vehicle until splashdown, and the recovery forces come in and take over after that.
Fire Room 1 is the launch control room we're going to use for Orion SLS for EM1 missions. We've been working with the Orion program to get the spacecraft data so we can process it with our software in the firing room, and we will be flight following that mission out of Fire Room 1. We refitted the room, we redid it, putting the sound suppression carpeting on the walls, making it kind of a more comfortable place to work. So we're aiming for about 50 people in Fire Room 1 for an EM1 mission. We are actually using Fire Room 1 right now to test Pad B subsystems.
This pad is going to be almost like a complete new pad because we will have refurbished each and every system that it's inside the pad. We're going to have the vehicle launch from the mobile launcher, and not only launch from the mobile launcher, but have a tower that will have all the services attached to the vehicle. The tower is going to be on the mobile launcher. The vehicle will be assembled at the VAB.
It's a return to a concept that we knew that worked very well during the Apollo years when the mobile launch platform had a tower on it. We knew that the VAB was designed to accommodate a launch tower on a mobile launch platform. We have to make sure that the VAB can remain adaptable and accommodate different vehicle architectures. And now we have a clean VAB shell, per se, the infrastructure, so that we can accommodate the new hardware, the new vehicle access with new platforms. And that is the first phase of what we're doing now.
And once the vehicle is ready with all the connections, the only thing we got to do is move the vehicle to the pad, do the connections to the mobile launcher. And once we do those connections, we're ready to launch.
There was a time where I had to explain what a crawler was. If you didn't work out here at the Space Center, or if you weren't in the Central Florida area, a lot of people just, somehow the vehicle got out to the pad. We knew what to expect from a load perspective with the new vehicle, the larger rocket and things along those lines. And that goes from the crawler lifted load, the hydraulics, also to the crawler way. We're going to have to increase the load lifting capability for the crawler way itself with the rock. What we've essentially done is keep all the same hydraulic components, but just increase the size, the diameter of the hydraulic cylinders. Last November, we actually took a ride out with the completed crawler 2 out to the pad and tested out the systems and a couple punch list items, but everything worked great. The control system had been upgraded. The driver's cab consoles had all been replaced. The brakes had all been replaced. Nearly every subsystem had some kind of work done to it. The traction support elements, each of the four corners has 22 rollers that are about the size of a car, to be honest with you, and we're changing out all of those, enlarging those as well.
What I love doing is reminding the outside world, whether it's within our government or especially the media, that has a perception that we're in a lull, there's nothing going on, that the space program's shutting down, to kind of dispel that rumor and say, no, this is the far opposite for us. We are utilizing this inter-program time frame to make all the modifications and all the infrastructure changes that it will help bring that agency vision into reality.
Many of us feel the country wants to go forward, and NASA has a big following, and every time I talk to people, they're excited about NASA.
Enabling people to go beyond where they have ever gone before and look and discover things that they didn't even know existed is it's just a real honor.
It's been a pleasure to be involved with this project, and I can't say enough for the team that's put this together.
I'm privileged to work this program. I think most people who are working it today feel the same way.
I can't believe they pay me for this job. It's just wonderful. It's great.
Perseverance sends more sounds from Mars. The rocket boosters for Artemis 1 are all stacked up, and preview of a weekend spacewalk. A few of the stories to tell you about this week at NASA. Our Mars Perseverance rover has beamed back more sounds it has collected since landing on the Red Planet on February 18th. In this latest batch of recordings made by the rover's SuperCam instrument, you can hear The first acoustic recording of a rock on Mars being struck by a laser. The rock was given the name Maz, the Navajo word for Mars. Some of the zapping sounds from the laser impacts are slightly louder than others. The variations in the intensity of the sounds can give researchers clues about the physical structure of the target. The SuperCam also recorded sounds of Martian wind noise captured while the mast that holds the rover's microphone was still stowed. The muffled sounds are reminiscent of what one might hear listening into a seashell at the beach or with a hand cupped over an ear. You can check out these sounds for yourself along with other sounds of exploration at nasa.gov/sounds. Engineers at our Kennedy Space Center have completed stacking the Space Launch System, or SLS, solid rocket boosters for our uncrewed Artemis 1 mission around the moon and back. The twin booster segments were stacked onto the mobile launcher over the course of several weeks. Following a successful hot fire test at our Stennis Space Center, now targeted for March 18th, the SLS's core stage will be shipped to Kennedy and stacked with the boosters and our Orion spacecraft in preparation for Artemis 1. The International Space Station's 5th spacewalk of the year is slated for March 13th. During the outing, NASA's Michael Hopkins and Victor Glover are scheduled to service and relocate some jumper cables of the station's thermal control system, continue some work from a January 27th spacewalk, and work on some other tasks. The outing is the 4th spacewalk for Glover and the 5th for Hopkins. NASA astronaut Mark Vande Hei has been assigned to the International Space Station's Expedition 6465 crew. He and cosmonauts Oleg Novitsky and Pyotr Dubrov of the Russian space agency Roscosmos are scheduled to launch April 9th from the Baikonur Cosmodrome in Kazakhstan. A collaboration between NASA, the U.S. Department of Agriculture, and George Mason University is making high-resolution NASA data on soil moisture available to agricultural and natural resources professionals who use soil moisture and other data to plan crop planting, forecast yields, track droughts or floods, and improve weather forecasts. The Crop Condition and Soil Moisture Analytics tool makes data from our Soil Moisture Active Passive mission and the Moderate Resolution Imaging Spectroradiometer instrument available in a user-friendly format. We teamed with American Aerospace Technologies Incorporated for a recent demonstration flight to simulate aerial inspections of gas and petroleum pipelines. NASA, the Federal Aviation Administration, and 3 industry partners are working together on demonstrations like this to show potential commercial applications of different-sized unmanned aircraft systems used in various locations and airspace classes. This research aims to accelerate the safe integration of these aerial vehicles for commercial applications into the national airspace system. That's what's up this week at NASA. For more on these and other stories, follow us on the web at nasa.gov/twan.
Immediately after the universe was born, it was too tiny and too hot for protons, electrons, and even photons to exist. Within a second, it had expanded and cooled enough for protons and neutrons, collectively called baryons, to form. Almost instantly, there was a rapid burst of sound waves triggered by tiny variations in this particle soup. Scientists call these waves baryon acoustic oscillations. The pressure waves traveled outward for 400,000 years until the universe thinned and cooled enough for light to travel through it. The universe became transparent and the waves froze in place. Over time, the denser regions formed by the waves encouraged more star and galaxy formation than other areas. The imprint of those waves expanded with the universe, slowly accelerating due to dark energy. Today, with our snapshot of the universe, there is a slight tendency for galaxies to be separated from each other by a distance related to that expanding ring radius. Although difficult to see, it is detectable as a slight bump through careful surveys of many galaxies.
A new era of exploration is beginning. NASA is building on its experience in low Earth orbit and preparing to go farther, setting up a base camp in orbit around the moon, known as the Gateway, exploring the surface of the moon like never before, and preparing to one day go to Mars. To accomplish all this, NASA will need a new spacesuit for its astronauts, one that's more flexible, versatile and durable than any made before. Engineers are now hard at work designing, building, and testing the new suit, making sure it's up to the task for future exploration. Some of the greatest moments in exploration have taken place with a human in a spacesuit. Whether it was a first journey outside the spacecraft or traversing mountainous moonscapes, the spacesuit made it possible. The act of sending a suited human outside the spacecraft is called EVA.
What is an EVA? EVA is an acronym that stands for extravehicular activity, which is what most people know as a spacewalk. It's whenever we take astronauts and we let them go outside to do useful work in the vacuum of space.
The spacesuits currently in use for NASA EVAs were designed in the 1970s for space shuttle missions. They have been upgraded over the years for work on the International Space Station and have served NASA well.
In the past 20 years, there are a handful of types of spacewalks that we've done. We've done planned spacewalks for maintenance. As hardware breaks, we can do contingency spacewalks. As technology improves, we can upgrade hardware. Or like with the Hubble Space Telescope, we're actually repairing very sensitive scientific experiments in order to enable science.
Those EVAs took place in microgravity, where astronauts float and need to use their hands to move from place to place. But moonwalkers, working in 1/6 Earth's gravity, will need spacesuits that let them use their hands and feet, walking to destinations and bending and reaching as they explore. For this new type of work, NASA has been testing prototype planetary suits, culminating in a new suit design, the XEMU.
The XEMU is Exploration Extravehicular Activity Mobility Unit. So it's an exploration spacesuit. So it's a spacesuit that you're going to use as we move forward on Gateway missions and on the lunar missions with Artemis. And then we're using all that to test the suits you would want to use to go to Mars in. So eventually you're going to have to be very independent and very confident in your hardware when you go and do a mission that far away from Earth.
One of the most obvious changes in the new spacesuit is the way astronauts get in and out of it. Donning the current suit is a multi-step process of wriggling into the upper torso and then getting help attaching a pair of space pants. The new generation spacesuit features a hatchback, where astronauts simply slide in and out of the one-piece body of the suit. Another big feature of the suit is the way the astronauts are able to move while wearing it. Apollo astronauts learned they had to hop to get around on the moon. The suit design sometimes made it difficult for the astronauts to work.
Up. Okay. We see that one went all the way in. Not quite. Like that.
Engineers learned valuable lessons from those Apollo suits. The improved design for the next generation spacesuit will allow astronauts to walk on the moon, not hop. Additionally, astronauts will experience an improved range of motion.
The new suits, the planetary walking suits we're working on now, we really hope to provide improved mobility and comfort along with reduced injury potential. And really, like I said, provide the best tool to the crew member that we can provide. Then we want to be able to provide them the ability to kneel down and pick up a rock, like they're going to want to do in their geology science that they're working on. We want this to be a very reliable and durable suit so they can use it day after day in a dusty environment and not have to do a lot of maintenance with it while they're needing to do their mission. So there's a lot of those kinds of aspects that go into improving the suit that we're going to provide for the lunar missions.
Improved mobility is not the only feature engineers have been working on. The astronauts will also be carrying a special backpack known as the PLIS.
So the PLIS is the Portable Life Support System. It's the backpack on the spacesuit, and it has all of the interesting parts to keep the crew member alive while they're on their spacewalk. So it has oxygen stored as pressurized gas for breathing, pressure regulators that regulate the oxygen pressure inside the spacesuit, and then a ventilation loop and a water loop that we call the thermal loop that provide trace contaminant and carbon dioxide removal from the breathing environment and also cooling for the crew member and the suit on board avionics and electronic systems.
While the Bliss has been on previous spacesuits, this improved version will offer new technology, greater control of its systems for the astronaut, and longer life for each EVA, allowing more exploration.
The Bliss labs are awesome, super fun places, and we physically assemble the parts to build the life support system, and then we test it. It's our opportunity to find things and fix things before we get it on orbit. We love what we do. We really want to see this system fly and be useful and help a person explore the moon in a more capable manner than they were able to do during Apollo. So it's a great job.
So I want you to perform some isolated joint movement to understand how the suit moves and then be out.
Testing for the new spacesuit continues underwater in the Neutral Buoyancy Lab. Here, the weightless environment of space can be simulated to put the suit through its paces.
So being able to test the suit in the pool and microgravity environments allows us to iterate on our design and make it better and get feedback from astronauts and from other instructors and trainers.
Could you reach all the way across and do the cross switches with your opposite arm?
Oh yeah, it's really easy to get all the switches with my opposite arm. I would rate this as excellent.
Come on. I know, I guess gotta get lower and flatter.
Yeah.
Hold on. Oh my God.
You did it! Very good.
So if this could happen in real life, this is a spectacular translation.
Rex and I are very lucky. It is like a brand new spacecraft.
Even has the new smell and everything.
It does. New car smell.
Spacesuits are also tested in the Active Response Gravity Offload System, or ARGOS.
Yeah, so the ARGOS electronically is able to tune an astronaut exactly to whatever gravity it is that we're practicing that day, whether that's microgravity, lunar gravity, or Martian gravity. The other nice thing about ARGOS is you're able to get the instructors and the engineers right next to the astronauts as they're working, helping the astronaut figure out a problem as they work through the development of that test for the suit or for a piece of hardware and get that real-time feedback.
Spacesuit hardware is not the only thing being tested on Earth. NASA is looking at human performance as an important factor in designing EVAs and spacesuits.
So related to a spacesuit, a lot of times people think about the actual engineering, the hardware, the different pieces, but I want to look at the EVA scenario from the human really inside the suit and make sure that their performance, both physically, cognitively, is going well. So we want to look at things like physical exertion, cognitive workload, injury risk, and really just trying to make sure that they're not impaired by the EVA system any more than they have to be.
The NASA team uses virtual reality technology, motion capture, and other tools to study what it takes for a human to conduct an EVA.
And what we're able to do is bring actual, no-kidding data to the table that really removes the opinions. That's probably our primary benefit for how we kind of enhance the EVA community is we take a look at this not from a hardware, not from an operations standpoint first. We look first at the human and then kind of say, what do they need to be able to do to be ready for the job?
All the work on the spacesuit here on Earth is building up to the ultimate test, to fly it in space.
So we're actually building a flight unit of that XEMU, and we're going to launch it to the International Space Station. And we will do an EVA with a current spacesuit, an EMU that we use today, and the XEMU with it. We'll go out in pairs, and we'll have the astronauts working together, one in the old suit and one in the new suit, and we'll test its functionality in a microgravity or a low-gravity environment out in the vacuum of space. That will help us test a lot of its systems.
The EVA on the space station will set the stage for the future, when the suit will need to perform a variety of missions beyond low Earth orbit.
Yeah, so a great example is NASA's Gateway. So even though it is in lunar orbit, it's still a microgravity platform. So
30 seconds and counting. T-minus 25 seconds. 20 seconds and counting. T-minus 15 seconds. Guidance is internal. 12, 11, 10, 9. Ignition sequence start. 5, 4, 3, 2, 1.
You're looking at the historic B-Test complex at NASA's Stennis Space Center, where we're about to do a second Green Run hot fire test, firing up the core stage of our new Space Launch System rocket. Good afternoon. I'm Lee D'Angelo. This stage we're testing today will be part of the rocket, which will soon launch from NASA's Kennedy Space Center on the Artemis 1 mission. That launch will send an uncrewed Orion spacecraft beyond the moon and back to Earth. It's the first flight of the Artemis program, which will return American astronauts to the moon and pave the way for exploration of Mars. The Space Launch System will be the most powerful rocket in the world and is the only rocket that can send the Orion spacecraft, astronauts, and supplies safely beyond the moon in one launch. Now, we first tested this core stage on January 16th. That marked a major milestone, firing all 4 Rs25 engines together for the first time for about a minute. However, it ended earlier than planned, so NASA and Boeing decided to do a second test.
And we gotta shut down.
Teams have been working hard to get to this point, and the test countdown actually started a couple of days ago. Here to update us on where things stand is NASA Public Affairs Officer Catherine Hamilton and Headquarters Green Run Manager Bill Robel in one of our test control centers here. Catherine?
Thanks, Lee. We're inside a secondary test complex outside of the control room, and we're listening in to provide you updates as the team progresses through their steps for this operation. We believe we're within about 45 minutes of the hot fire. The team actually started 2 days ago powering up the avionics on March 16th, and they checked out all the systems that they had tested on previous tests. Earlier this morning, they conducted a go-no-go poll to proceed into the test, and I have Bill Robel here with me to tell us a little bit more. Bill, can you tell us about how the operations have progressed today?
Yeah, sure will. So at this point, we've been in kind of replenish mode for both the liquid oxygen and liquid hydrogen. We've got, at this point, 540,000 gallons of liquid hydrogen on board and another 200,000 gallons of liquid oxygen on board. And they're in the conditioning process right now, where we're trying to get that temperature down as low as we can, get it within the start box. And we're also doing the same thing on the engine side of things. And what's important about all of this is that, you know, this timeline that we're going through here will help inform the operations that'll take place down at Kennedy Space Center, where not only do they have these things to worry about, but then they've also got to do the things where they're getting people on board and taking care of all the other extraneous things that they have to do down there. So for us here, right, we've also been monitoring things like the battery charging. They're basically up to speed at this point. And then we've got the redundant inertial navigation unit wet checkout, which is basically, you know, mounted up in the LOX dome area. And so they're looking to see how it behaves relative to the low temperatures that we're seeing now in that compartment. And so at this point too, the teams are basically looking at all their data, making sure that their systems are where they're supposed to be and ready to go for proceeding into the terminal account.
Thanks, Bill. And can you tell us a bit how the timeline is different for today's test than for a launch, and how is determining the time of the hot fire different from, you know, setting the time for a launch?
Yeah, so for us, it's actually we're in a pretty good spot. We're trying to at this point maximize the amount of commodities that we've got here in the test facility. So we're playing a little bit of a game where we've got crews that have been on for a number of hours, and at 12 hours roughly, they'll time out. We want to make sure that we don't have to end the operation any earlier than that, so we're really trying to maximize that. So they're in the process of working that with the nitrogen and helium, liquid oxygen, and liquid hydrogen. The other part of it is, right, the beauty of us is we're in a test. We're not going anywhere today. And so we don't have a destination. Our destination is right here. And so the difference right at Kennedy is they've got, you know, the orbital mechanics, their destination as to where they're going to go. And so they have to work basically all those details in to their exact launch window. Our launch window is basically when we start the test, and that doesn't matter too much today. But they do have a, you know, they've got a real time hack that they have to hit. So they'll have built-in holds into their process and procedures down there, and that'll inform them kind of how they move through the next steps. We just are fortunate we don't have to worry about that today.
Great, thanks. So that means that we don't have a specific hot fire target time right now at this moment, but we'll keep listening in and we'll provide updates. We do know that the test remains to be projected within the test window, and we believe we're within about 45 minutes. And so we'll continue to listen in here, and I'll turn it back to Lee.
Thanks, Catherine and Bill. And we will come back to you in just a few minutes, like you said, to take us all the way to the test, or sooner if you have any updates for us. We will be listening in, and I'll head right back to you if you do. Now, if you are just joining us, welcome. We're live at NASA's Stennis Space Center in Mississippi, and we're following the second Green Run hot fire test of the Space Launch System rocket's core stage. The core stage is the center core of the rocket that includes 2 propellant tanks and 4 Rs25 engines, miles of cables, all of the avionics, electronics, computers, the brains of the rocket, and all of the plumbing that work together to launch the rocket during the first 8 minutes of the mission. The green in Green Run refers to new, untested rocket hardware. So this is a comprehensive series of tests of all the core stage hardware for the SLS rocket to demonstrate it's ready for launch, culminating with today's hot fire. The core stage will power every SLS mission. So this test is important not just for Artemis 1, but for all future SLS launches as well. Those Rs25 engines are expected to fire up shortly here at Stennis Space Center. Before that happens, let's get a closer look at the Space Launch System rocket. Artemis is super heavy lift rocket and provides the foundation for human exploration and scientific missions to the Moon, Mars, and beyond. Powered by 2 solid rocket boosters and 4 Rs25 engines, this rocket provides unprecedented power and capability. Designed to reach 23 times the speed of sound and an altitude of more than 100 miles in just over 8 minutes, offering more energy, volume capacity, and payload mass than any rocket built today. Under the launch abort system, Orion, and the upper stage, and between 2 solid rocket boosters is the heart of every SLS configuration, the core stage. Towering 212 feet with a diameter of 27.6 feet, and storing 537,000 gallons of liquid hydrogen and 196,000 gallons of liquid oxygen, this is the world's largest core stage ever built. The core stage for Artemis 1 fires up for the first time at NASA's historic B-2 test stand. The core stage was designed by NASA's SLS program at our Marshall Space Flight Center in Huntsville, Alabama. Then built by lead contractor Boeing, using state-of-the-art manufacturing just down the road at NASA's Michoud Assembly Facility in my hometown, New Orleans. It includes engines manufactured by Aerojet Rocketdyne, with contributions from more than 1,100 large and small businesses in 44 states. It was shipped up here to Stennis on the Pegasus barge in January of last year, and then installed on the B-2 test stand where you see it here today. Engineers then began activating the stage's components one by one and taking it through the series of tests that make up the Green Run over the past year. Each test built upon the previous one and added a little more complexity. So today's hot fire builds on all of that work for a full test of the entire integrated system that will simulate all parts of the core stage working together during launch. Today's test will take us from extreme cold to extreme hot as the team loads cryogenic, or super cold propellants, into the fuel tanks and then fires up the engines to drain the propellant from the tanks to simulate launch. Now, the hottest part of the test today will be those 4 Rs25 engines at the bottom of the core stage. These Rs25s we are testing today are repurposed from the shuttle program. These 4 engines flew on some pretty iconic shuttle missions, including one of the Hubble Space Telescope's servicing missions, the historic return to space of Mercury astronaut and Senator John Glenn, 6 flights to the space station, and the final shuttle space mission in 2011. So you can trace a direct line from that final shuttle flight to the first flight of SLS. We've worked with our partners at Aerojet Rocketdyne to upgrade the 16 shuttle main engines, which will power the first 4 Artemis flights. And now we're building 24 new engines using 3D printing and other manufacturing innovations to reduce cost, complexity, and manufacturing time. Of course, all of this work is building towards that Artemis 1 launch from Kennedy Space Center later this year. Here's a closer look at that mission and how it paves the way for future exploration beyond.
3, 2, 1, 0. Mission liftoff.
Artemis 1 will lift off from Launch Pad 39B at NASA's Kennedy Space Center in Florida with 8.8 million pounds of thrust, provided by the most powerful rocket in the world, our Space Launch System rocket, or SLS. The uncrewed flight will be the first integrated test of SLS, our new Orion spacecraft, and exploration ground systems at Kennedy. Artemis 1 will send Orion beyond the moon, 280,000 miles from Earth, farther than any human spacecraft has ever flown.
This is not NASA doing this. This is the United States of America doing this program, the Artemis program, and there are companies all across our country that have a part in it, so there is kind of this wave of excitement being generated just by saying, we're going back to the moon.
After the upper stage of the rocket separates from Orion, the upper stage will deploy small satellites over several days to perform science experiments and technology demonstrations. Orion will make its multi-day outbound trip to the moon, propelled by a service module provided by the European Space Agency. Engineers will test Orion's systems on the way to the moon. Then, Orion will fly about 60 miles above the lunar surface, using the moon's gravity and engines on the service module to enter a lunar orbit. After about a month and a total distance of over 1 million miles, Orion will return home, faster and hotter than any spacecraft has before. A primary goal of Artemis 1, ensure Orion safely returns to Earth before we fly with humans. When we do, we'll build our capability for sustainable lunar exploration, preparing us for missions farther into the solar system.
Initially, what we'd like to do is start establishing a presence on the moon. So we're going to establish going back there on a regular basis, and then we'll end up setting up Gateway, and we would launch to the Gateway, and from Gateway, land on the surface of the moon.
We are there for, weeks, months on end. And there, we're going to be able to test out all the hardware and the habitats and the hatches and the suits and the rovers that'll allow us to prove out those technologies. The moon will lead the way to Mars, and we should be there, within the next couple of decades.
Just amazing. And now we are going to hand things over to Catherine and Bill again in the control center. Catherine?
Thanks, Lee. We are in the secondary test control and outside the control room here listening in so that we can provide you updates. Bill, can you give us an update on how things are progressing?
Yeah, so they're in the process now of going through the final checks. Everything's really nicely going really great today. So everything's right on schedule, nominal. They're trying to do this thing what they call right now is jump the clock, which is trying to work it a little bit ahead. So they're in the process of resetting the clock and making sure that when they get to that 10-minute point that it doesn't continue to count down, because that's where they have to go with that pole well ahead of that. So they're working on setting that stuff up right now.
All right. So we'll continue to stand by and listen and provide updates. And as Lee mentioned earlier, the team previously conducted a hot fire test in January. The engines did shut down earlier than planned during that test, but the January 16th test successfully completed several operations for the first time. They were able to transition to the automated launch sequence operated by the core stage flight computer and the green run test software. They completed the terminal countdown sequence that is like the launch countdown. They also pressurized the tanks and delivered the propellant to the engines and demonstrated the performance of the core stage's main propulsion system, firing the engines at 109% power, and they operated the thrust vector control system that steers the engines. So it's a smooth countdown so far today, and we'll keep standing by. We'll take a pause for a moment, and we'll check back in just a few minutes. The B1, B2 test stand that you're seeing there is a dual position vertical firing facility, with the B1 side equipped for single engine tests and the B2 side designed for rocket stages. The stand is anchored to the ground with 144 feet of steel and concrete. We talked a little bit about the history of the Rs25 engines, and the B2 stand, which is where the SLS core stage is secured now, also has quite a bit of history. It was used in the 1960s to test Saturn V rocket stages that carried humans to the moon during the Apollo program. And the Space Shuttle main propulsion test article, consisting of an external tank and 3 main engines linked together with a simulated shuttle orbiter, was also tested on the B2 stand. The B2 stand has been modified to test the SLS core stage for the Artemis program that will return humans to the moon, with a new steel superstructure added for testing the SLS core stage. The stand is now almost 350 feet high, ranking it as one of the tallest structures in the state of Mississippi. For a little bit more about the Rs25 engines, each of the Rs25 engines is about the size of a compact car if the engine were turned on its side. Standing up, they are each 14 feet tall and 8 feet in diameter. They each weigh about 8,000 pounds. The Rs25 is designed to operate in extreme temperatures from negative 423 degrees Fahrenheit to 6,000 degrees Fahrenheit. And as Lee mentioned, today's test will go from extreme cold to extreme hot. When the hot gases exit the Rs25's nozzle, they travel at 13 times the speed of sound, which is fast enough to travel from Los Angeles to New York City in about 15 minutes. The core stage itself stands 212 feet tall and at a diameter of 27.6 feet and weighs about 2.3 million pounds when loaded with propellants. So the next major milestone coming up will be the poll for the terminal count. It's the last 10 minutes of the countdown. Bill, can you tell us a little bit about what we can expect to hear during the terminal count?
Yeah, so just ahead of terminal count, we'll hopefully get that call. They'll do a poll, which is all the members of the team basically getting their go for going into that terminal count sequencer. And then once we actually get into it, there's at least 500 different events that take place in that last 10 minutes. So I'll not go through each one of those with you, but there are some pretty good ones I think that highlight, kind of what the major ones should be or are. We've got to terminate the hydrogen replenish, and then we've also got to go into the hydrogen tank pre-press operations, which is where they'll pressurize the hydrogen tank. It'll start doing that on its own as well. Initiate ground helium spin start supply to the CAPUs. So initially when the CAPUs come up, they'll be running off of the helium supply in the stand, and then it'll switch over to the engines when they come up as part of the plus count.
Can you tell us a little bit about what the CAPUs are?
Yeah, so that's the core stage auxiliary power units. They're variants of the ones that were flown on shuttle. The difference is that where those were hydrazine powered, these are basically run off inert gas and then into hydrogen off of the engines when they get into the plus count. So it's basically a turbine system that spins a pump, and that pump then in turn pressurizes the oil in that system. And through a series of valves and commands, they could then go ahead and actuate the actuators that are mounted to each of the engines in pitch and yaw. After that, we'll get into liquid oxygen terminate, and liquid oxygen replenish will stop that operation. And then we'll go into CAPU starts, and that's where each one of those core stage auxiliary power units would be powered up. And that takes, on the order of about 30 seconds to bring each one of those units up. They're done individually. And then they basically move into transitioning into the LOX tank pressurization operations. They do a TVC gimbal profile on helium, so that's actually something different that you won't see in the plus count. In other words, we do a lot of actuation of the TVC system in that, but we don't move it as far because of the limits we've got in the stand for how far you're moving it relative to having, the engines burning at that time. So in the pre-count, we'll basically get the full movement, the full gimbal, full displacement, and then once they get into the plus count, they will not do that, but they'll do some other things. And then after that's complete, they'll basically bring the actuators into their null positions. Basically, they'll go ahead and make sure the engines are ready to go ahead and start. They will then transition the core stage to internal power. They do have, with the redundant inertial navigation unit, they've got the gyro compass alignment that they'll finish up. And that's when we get into the next big sequence, which is the go for the automated launch sequencer, and that'll start roughly at 33 seconds. So that's kind of the big steps that take place up to that point. And what happens once we get into that ALS is that if we have to recycle, then that's a big deal. It's probably not something we can recover from that easily on day of. But ahead of that, we can basically recycle back to the 10-minute mark, and then it would take us probably an hour or two to get back into position where we could go through it again, but that's kind of how the day would look.
Thank you. So it sounds like the majority of the calls are actually going to come in the last 5 minutes of the terminal count. And so we're waiting to hear when we are ready for the poll for the go, no go into the terminal count. So we'll stand by for a little bit here, and then we'll come back when we have another update. For the Artemis 1 launch, there will be a built-in hold before the go-no-go pull to go into the terminal count with the last 10 minutes of the countdown. This isn't quite the same, but it is similar. The team takes a look at the data from the vehicle and the facility and ensures that everything looks good before proceeding into the terminal count. So we're just a little more than 10 minutes away from our T0 time now to fire up the engines. And when those engines fire up, the team is looking to get at least 4 minutes of data to support the test objectives needed to confirm that SLS is ready to launch Artemis missions. From there, they will continue to let the engines fire and to burn through all of the fuel in the tanks and possibly pick up additional data for some secondary test objectives. During launch and ascent for Artemis missions, we expect the engines to fire for about 8 minutes to drain the tanks of the propellant before what is called the main engine cutoff, or MECO. So, Bill, tell us a little bit about what we can expect after hot fire starts.
Okay, so the other thing I'd say is I'm also listening in, so if we get to the point where they're going to call for the poll, I'll just tell you to pick it up at that point. But so where I left off was with the ALS start, so that's roughly 30 seconds before they actually start. We would then bring on the hydrogen burn-off igniters, which are basically a series of flares that are built into the stand to pick up any residual hydrogen and basically dissipate all that. They'll finish with the renew redundant inertial alignment navigation mode, and then basically they go into, at roughly 6 minutes, they'll do the Rs25 starts, and those they bring up one at a time, and roughly at 5-6 seconds they'll start that. At 1 second they'll be up and running at 100%, and with that, I think we're getting ready to hear them go for the poll. But as they basically get through that part of it, we'll hear the basically the engines will come up to 109% thrust level, and then we'll go into the first poll at the gimbal profile. So I think what we should do at this point is switch over, if we can, to pick that part of it up.
All right, let's listen in to the poll.
That's the correct time pack as the sequencer steps through there. Reminder to everybody, after we get past 557 and after we terminate LH2 system securing, we only have 2 minutes 35 seconds of full time before we have to recycle pack. Also, another reminder to everybody, when we do the switch to internal power, we will get the Christmas tree effect on the avionics screen. So that is normal, that is to be expected. So just remind everybody that we will get that Christmas tree effect once we go into internal power. All right, sequencer, on your command, let's go ahead and initiate the terminal count sequencer for substep alpha and record the UTC time, please.
Copy. Okay. T count has resumed.
And give us a UTC real quick, please.
20, 2712.
Copy, 077, 20, 2712.
Do you copy?
T-minus 9 minutes.
All right, it sounds like we actually missed the poll, so we are in the terminal count sequence now, and we are standing by and listening as they progress through their steps.
T-minus 8 minutes. T-minus 7 minutes.
LDS, place your recorders into continuous.
And we're about 6.5 minutes away from hot fire right now.
And T-minus 6 minutes, starting LH2 securing. T-minus 5 minutes, initiating TVC spin start.
Yeah, so at this point, they've basically initiated CAPU start, and basically those will be coming up on helium. They'll go into a what we call the wiggle test, which is where they'll gimbal the engines, and then so that's basically coming up here in just a couple of minutes. On the plus side of that, you know, once we get into the engine starts.
T-minus 4 minutes, CAPU start, starting LO2 securing.
Okay, so LO2 is being secured now, so that they're really moving forward in the plus count here. Still roughly at T-minus 3 minutes 42 seconds. And so with that, we should be seeing the TVC gimbal profile here in about half a minute or so. Basically at this point they've got the water system all turned on. So you might be able to see that in some of the views, and that'll basically take care of not only the heat coming off of the engines, but also dampen the tremendous amount of noise that'll be coming off. As mentioned earlier, the hydrogen burn-off igniters will come on at about 12 seconds.
T-minus 3 minutes starting PSN 4.
The inertial navigation mode will be complete at about T-minus 10 seconds. And then basically the enable command for ALS at 9.2 seconds. And then we go into engine start roughly at 6 seconds. Those take about 5 seconds to come up to full operating pressures. And basically at that point, the stage controller will be go for launch, or go for test in this case, at 2 seconds. And basically we go forward into our profile for the day.
All right, we're coming up on 2 minutes.
There's a gimbal test taking place now.
T-minus 2 minutes.
So the call was they just announced at T-minus 2 minutes, which is basically they have finished the gimbal test with the actuators and they're bringing them back into the null position. And then basically at this point they basically are getting ready for powering up the engines. Again, core stage transitions to internal power at roughly 1 minute and 30 seconds out.
T-minus 130, switch to internal power.
And then if Reno gyro compass alignment converges at roughly 1 minute. And then we'll have the go for ALS, and we'll clear that polar shortly at T-minus 33 seconds.
T-minus 1 minute following personnel report go, no go for ALS, AEA, PEA,
Go.
AGA,
Go.
REA,
Go.
NEA,
Go.
NTC. Vehicle and speed-use systems are go for ALS.
And you, at this point you see basically the water system has come on full bore.
All right, T-minus 30, we're in ALS.
And you just got the official start of ALS. Next up is the hydrogen burn-off igniters come on at 12 seconds before T0.
FRS, red line back to H-boys on.
Go for engine start.
H-boys are on and engine starts has been okay.
And all personnel, we've got engine start and we're into the plus count. All personnel, please continue to monitor your system, and grass is in control. Plus 60 seconds starting TBC profile number 1. Again, first now we've got a fire indicator. Everyone go ahead and ATS. So ATS. Okay, copy. Do you want me to hold down ATS? I copy that. You cancel it out. Yeah, profile. Remember. Starting the FRT profile.
We're about 3.5 minutes into the plus count.
Camera's number's still good. That's a facility issue. And we'll see it works out. Puts 4 minutes 30 seconds. I'll shoot in the FRT profile. Hot light at 16. Plus 5 minutes.
We're just over 5.5 minutes in the plus count.
About 6 minutes. Dominate from Michael 16. Yeah, I'm not seeing any PCC violations, so copy, we're good. Thanks, sir.
We're coming up on 7 minutes of the plus count.
T plus 7 minutes. And T plus 7 minutes, 30 seconds, starting TVC profile number 2. T plus 8 minutes. And then the TVC profile number 2.
All right, so we're just over 8 minutes into the plus count.
Well, personnel is coming up hopefully on the last depletion here, and we have a cutoff. All right. REA, can you verify REA on channel 16? REA on channel 16, verify. Safe engine shutdown, please.
Safe engine shutdown.
And your input shutdown standby, correct?
Correct.
Okay, all personnel, that takes us to page 656. All personnel go to page 656 to start the post-hot fire shutdown securing operations.
All right.
Okay, all personnel on page
Bill, as you said earlier, as we talked about earlier, the team was hoping to get at least 4 minutes of data. And we... All right, they are proceeding with their shutdown procedures now. As we said earlier, the team was hoping to get at least 4 minutes of data, and they did get more than 8 minutes, excuse me. So they should have gotten what they need. The team will obviously need to look at that data, but based on what we've seen, Bill, tell us more about what it looked like to you.
Yeah, so they clearly got the full duration that they were after, which is really great news. And I think you heard the applause. They had, the commanded shutdown, which is exactly what they were looking for. They had no TCC violations, test commit criteria violations that would have prompted an early shutdown. So that was really good news. Clearly there's a lot of data that's going to have to be analyzed. The engineers got to see what worked and what didn't, or what needs to be tweaked and what doesn't. But that said, I think the applause says a lot about how the team feels, that they got through the test, and it looks pretty good right now. Yeah, so there was some, observed burning on the aft end. One of the things that Boeing had done after the last test was to apply a lot of extra cork to the aft end, because we didn't, unfortunately, with this test, right, we're not flying through the thin air as we ascend, and so we knew we were going to have more of that, and that was one of the reasons why they added that. They also put a tape covering over the top of that. We knew that, if the tape gets hot enough, that adhesive layer below the tape surface is going to start burning, and so we clearly saw a lot of that, but there was nothing that prompted a shutdown early, which was really good news.
Great, thank you, Bill. I think that's all the updates that we'll have for you here as the team proceeds through their shutdown procedures. So we'll turn it back over to Lee.
Thank you, Catherine. Congratulations to the team. So as the engineers gather the data from today, we look ahead to the next steps. This core stage will be refurbished and sent by barge to our Kennedy Space Center in Florida. There, it will be stacked in the iconic vehicle assembly building with other elements of the SLS rocket, including the twin solid rocket boosters, which our teams have already begun stacking on the mobile launcher. The core stage and boosters will then be stacked with the upper stage and the Orion spacecraft. All of this work putting us on track to roll out to Launch Pad 39B for a liftoff later this year on Artemis 1. We've got several other firsts on the horizon. This year, the first of our commercial lunar payload services, or CLPS missions, begin with 2 companies delivering instruments to the lunar surface. The golf cart-sized Viper rover will search for water at the moon's south pole. And a small CubeSat called Capstone will head to the moon, scouting the orbit to be used on later human missions. Meanwhile, the hardware for the next 2 Artemis missions, which will carry astronauts to the moon, is coming together. The Orion spacecraft for Artemis 2 is down at Kennedy undergoing assembly, and the spacecraft for Artemis 3, as well as the rockets for Artemis 2 and 3, are also being manufactured right now at Michoud. So that wraps it up for us here today. After a major milestone on America's return of astronauts to the lunar surface, a successful test of the core stage of the Space Launch System rocket. Up next, we'll be replaying the test, and we will have a post-test briefing in about 2 hours here on NASA television. We invite you to follow all of our progress online at nasa.gov/Artemis program, or join the conversation online with @NASA-Artemis and @NASA_SLS. Thank you for joining us, and go Artemis.
And all personnel, we've got engine start, and we're into the plus count. All personnel, please continue to monitor your systems, and grass is in control. Plus 67